Hello friends, today I'm going to show you how to create a 230 volt incandescent lamp dimmer using sine wave phase shifting using a diode bridge and PWM. So first let's design the circuit and then let's test the actual circuit with the PWM generator. For this you need a PWM generator. The PWM generator that we created a couple of videos back that uses an ESP8266 controller, the Wi-Fi controller, and we created a web-based PWM firmware for that ESP82266 controller. So I recommend you to go ahead and check that video before coming to this one. So first let's design the circuit using Proteus, which is a circuit design software, and then let's do the actual circuit. So friends, let's go ahead and start the Proteus. So let's get a new simulation. Alright, now I'm going to place some components here. So we need a diode. So let's use a 5408 diode which has a high voltage, right? So let me double click, and we need a alternator to simulate the sine source. Alternator, right, and we need a lamp. Okay, so also we need a FET. So in real we are going to use 13N50 FET, but in Proteus we are going to use IRF 720. So let's get that. Alright, so this is the FET. And also we need PC817, the optoisolator. So this is the optoisolator, and also we need a DC voltage. Let me go ahead and check. So this is DC voltage source, the battery. So let's start designing. All right. So now I'm going to create the diode bridge. So let me zoom in. So I place one diode like this in this direction and the other in the reverse direction. Alright, and same like the above. So, and I connect these two ends. So this is our live and this is the neutral. Alright, so let me get my alternator here. So we are going to simulate the sine wave here, and let me change the voltage to 230 volts, and our frequency is 50 hertz. So let's set that up, and this is the live neutral. So I'm going to place one line here. And so in traditional bridge rectification we are placing this wire like this, but in our phase shifting we are not going to use that kind of wiring. Instead we use this lamp in series with the diode bridge. So let me rotate now. So in series with the diode bridge we use this lamp. So of course I need to increase the voltage of this lamp. So let's set to 230 volts. So like this, and right now if we play this, you see nothing happens. So now we need to connect the DC side. Alright, so obviously this diode and this diode should be shorted together, and same for these two also should be shorted together. So this is our DC plus, so basically 230 volt plus line, and this is the ground line. Alright, so now let's get a switch here in order to test this. So I'm going to push button switch here. So if we short this DC minus and DC plus through this switch, you will notice this LED, this lamp turns on. You see, this lamp turns on. So this is the phenomenon that we are going to use to dim this incandescent lamp. So now, instead of this short circuit switching, and let's use our IRF 720 MOSFET. Alright, so now let me change that. So here, now we should connect the MOSFET into this DC side. Alright, so this side of the MOSFET, this top pin, is the drain pin. So the drain pin goes to the positive side of the DC power supply, which means this line. So let's connect that. Now this is the source. So the source goes to negative side of the DC power line. Alright, so that is this one. Alright, so I forgot. So we need one more item. So that is 10K resistor here. So the 10K resistor is responsible for grounding the gate terminal when there is no voltage applied to stop it from floating. Alright, so let's get 10K from here and let's ground this pin. Alright, so this is our negative side, so let's connect that. Alright, now without any voltage, so when the gate pin has no voltage, this resistor pulls the gate down to the ground. Alright, so if we run this, you see nothing happens. But if I get this battery source, so before we discussing this battery, let's discuss some characteristics of this FET. Alright, so you see we are going to control a 230 volt lamp here. So this FET, so these all are having 230 volts. So this FET should be able to handle that much of voltage. So IRF 720 FET that can, so if we check the data sheet here, so if we type IRF 720, so we get this data sheet. So let's go ahead and check this data sheet. So if we check this data sheet, so you'll notice that the first pin is gate and the second, third pins are drain and source. Alright, so if we check this table, you see the maximum voltage of the drain and source. Alright, so the drain source voltage, so this is 400 volts, so we are using a 230 volt system, so we can definitely go ahead. So that's it. So we can use this FET in order to control our incandescent lamp. Alright, so but in real circuit we are going to use a different FET. So this is for simulation, so in simulation you can use any FET, but let's have a look at the FET that we are going to use in the real system. Alright, so let me close this one. So that is 13 and 50. This is the FET that we are going to use. Alright, so let's see the characteristic of this FET. Alright, so this is the FET that we are going to use in the real circuit. Alright, so as you can see, the first pin is gate, so the second one is drain. As you can see, the second one is drain, third one is source. So the same arrangement can be followed for this FET too. So now here let's see the maximum ratings, maximum voltages. So in here we have a drain source voltage is maximum is 500 volts. Alright, so we are already safe because we are using a 230 volt system. So and this parameter also required, you can see this RDS on is 0.48 ohms at VGS 10 volt, which means if you apply 10 volts between the gate and source, which means gate and ground terminal, you get 0.48 ohms or 480 milliohms between drain and source. So if you apply 10 volts between these two, you get 0.48 ohms in these two. Alright, so if we apply to this circuit, alright, so if we apply 10 volts to this, the resistance between these two lines get 480 milliohms. So which means these two lines are effectively shorted together, rendering this bulb to turn on. Alright, now here we are going to supply 12 volts. So as in data sheet, this gate voltage can go up to 30 volts here, so no problem, we can directly supply to 12 here. So with this battery is here, if I connect this ground into the common ground of this circuit, alright, and positive to the gate like this, as you can see, this bulb turns on. If we remove this, you can see the bulb no longer active. So now, since we are using a PWM controller to generate PWM to this side, we are going to use a opto isolator in order to isolate the low voltage PWM controller and this high voltage circuit. So our opto isolator is PC817, so this is the opto isolator. So now let's place it like this, alright, so like this. So let me tell you how this works. So if we apply some voltage to between this first and second pins, this LED turns on internally in the opto isolator, alright. When the LED is turned on, this side, the pins in 3 and 4, this is a transistor, and as you can see, there is no base pin here. So the base is actually the photosensitive base that sensitive to this LED. So when this LED turns on, this base get activated because of the lights from this LED, and when the base is activated, the current can flow from collector to emitter. Alright, so that's how we are going to isolate the circuit. So the isolation between these two sections are around 5000 volts. So we are going to use 12 here, alright. Maximum is 240 here, but this one around 5 or maximum 5, so no problem there. So let me connect this terminal, this positive terminal, to the collector here. So collector is always in the positive line, and I connect the emitter to the gate. Alright, so what happens is, when we provide the voltage here, when the LED turns on, this get biased, so the current from collector, so this current flows through the collector and goes through emitter and to the gate, and bias this FET and shorting these two lines and come back to the ground of the battery. Alright, so this is the basis of the PWM generation using sine phase shifting in this circuit. So if we try to start this thing, so as you can see, we got a problem with the starting. That means the simulator cannot run this simulation. Alright, so we got error here, so that means something about the stepping size is too strong. So now this is the PWM input, and we are going to make this in the actual circuit, and we can simulate it from there. Alright, so I'm going to use this opto isolator here. Alright, so I'm going to use this 12 volt source. Alright, and this one is same, this is same, also the 10k resistance is also same, and I'm going to use a 230 volt input to this alternator, and I'm going to use a normal incandescent light, so this will be a holder. Alright, and this will be changed to 13N50 MOSFET. Alright, so let's go ahead and check the real circuit. So friends, this is the circuit that we designed in the Proteus. So this is the diode bridge that we mentioned and this is the MOSFET transistor, and this is not in the design. This was just to do some testing. Actually, this is a fuse box to in order to short this diode bridge while we are testing. All right. So this is the gate pull down resistor that we included in our design also, and this is the gate pulse. All right, and of course this is the holder to the incandescent bulb that series with the diode bridge. So of course this is the main voltage in. So the main voltage goes through this track and it crosses this holder and goes to the diode bridge, and from this end the DC end. So in my case this will be the DC end. So in this DC end the positive side of this diode bridge is these two pins and the negative side is these two pins. So the drain is goes to the positive side, which is this middle pin of this MOSFET, and the source side in the MOSFET. All right, so this is the gate, of course. So this is the PC817 opto-isolator. So this side, as you can see, this is the 12 volt inline. So the incoming 12 volts goes here and it goes to this diode is PC817 opto isolator, and this is the PWM input to the PC817 opto isolator. So the incoming PWM turns on the light in this PC817. Due to the light turns on, this emitter and collector get biased and the incoming voltage can go through this gate and come back to the 12 volts terminal. So now this is the actual circuit of the design that we designed in the project. So let's go ahead and test this thing out. So of course I'm going to connect the PWM and the 12 volts in and the incandescent lamp, and let's give 230 volt and check this out. Hello friends, so I made the connection. So as you can see, this is my 12 volt power in. So simply this is a voltage step up from my 5 volt power bank, and here I connected the PWM channel right here from this ESP8266. This web-based PWM controller we created a couple of videos back, so I recommend that you go ahead and check that video. And this bulb of course connected, and this plug connected. So let's now connect to our Wi-Fi PWM. So since now it's already connected there, so let me turn on the power to the incandescent lamp. So notice there's nothing at this moment. So let's go ahead and let's go and refresh this page. So as you can see, now it's jumped to center. So if I increase and decrease this, so as you can see, when we increase the slider we get the higher brightness, and we decrease this we get the lower brightness. So this uses sine wave phase shifting with those diodes. So this is what I wanted to share with you. So that's all for this video. So I hope you enjoyed this video. So click a like button if you like the video, and don't forget to subscribe to my channel, that is Fun Text with Hashan, and also make sure to click the bell icon so you will be notified when I uploaded a new video. So thanks for watching and thank you very much.